I'm Jonathan Tonkin from the University of Illinois. Seen from space, Earth is a world of water, so it seemed quite incredible that we might be running out. Our societies run on water, far more than just to drink. We need it for agriculture, for energy, and for industry. This week, we'll look at water's role and find out if there will be enough in the 21st century. Before we get started, I'd like to make a point about units. In most places in the world, litres are used. A litre is about 1/4 of a gallon if you're from the United States. Another measurement I'll be using is cubic metres of water or cubic kilometres of water. A cubic metre of water is 1,000 litres, and a cubic kilometre of water is 10 to the 12 litres or a teralitre. That's a lot of water. Now, we know that water is renewable, but it can also be used unsustainably, even though it is a renewable resource. How is this possible? We need to know a little bit of background on how water works in the Earth system. It's renewable because it's powered by the sun, which evaporates waters from the oceans. Then gravity cycles that evaporated water back to the oceans. So the water gets evaporated and then falls as precipitation and then flows towards the oceans. Over 400 cubic kilometres per year, that's over 400 teralitres, or 100 million gallons of water is evaporated each year in the Earth system. So that's an enormous amount of water. Most of that water gets returned directly to the oceans in the form of precipitation, normally rain. Some of that water falls as rain or snow over the land, and here it can enter places where humans can use it. We see water flowing back towards the oceans both overland, which is what we're used to seeing in the form of rivers, but it turns out there's another enormous resource of water which is hidden beneath our feet in aquifers. Water flows under the ground in groundwater flow. So this water is also very important because humans tap into this water when we do things like grow crops or capture water for energy use or industry. These water fluxes, that is the water flows, give us a sense of how much water we can use each year sustainably. We can use the water as it moves through the Earth system in that hydrologic cycle, and then when it gets returned to the oceans, it re-enters the hydrologic cycle. Of course, if we take too much water out, then we can reduce the stocks of water and not just take the flow of water. Take the Rio Grande as an example. This is a river in North America which has only about 20% of its water left by the time it reaches the ocean. The rest is taken out for human use. This isn't an especially sustainable use because this changes the ecosystems, and so there's an impact on the natural world when humans take out a large percentage of this normal flow. So, just a note on terminology. Flux means flow, and that's an amount over a given period of time. So you could have 100 cubic kilometres per year, 5 gallons per second, an amount divided by time. But we use more water from the Earth system than just this flux. We also use stocks of water. You can think of a flux as like an income. This is how much money you make per year. But if you have a bank account with some money saved, that might be your stock of money. So similarly, you can spend more money in a month than you make in a month if you take money out of your savings. In many places around the world, this is what people are doing with water. We're not just taking out the amount of flux or flow that comes through the system, we're also subtracting from stocks. Where are these stocks? Well, the biggest single storage place for water at the surface of the Earth is, of course, the oceans. That has over 1 million cubic kilometres, or 1 million litres of water. Most of this water is not usable, of course, for humans unless it's expensively treated because it's salty. So if we look at freshwater stocks and we exclude the biggest places, the glaciers, the polar ice caps have far more fresh water in them than any other source. We have lakes and dams at the surface. And they have about as much as travels through the surface and subsurface systems every couple of years. So the total stock in lakes and dams is comparable to the flow for each year or two. But groundwater stores much, much more. And so in a sense, we have a hidden ocean beneath our feet. And unlike the actual ocean, this water is fresh. So if we extract this water, we can use it in things that we need. We can drink it, we can use it to water our crops and so on. This stock took a long time to in place. And in fact, in some places, the water under the ground is thousands of years old. So it could take millennia to replace if we extract this water and faster than the natural flow would replace it. There's lots of incentive to use this groundwater. Worldwide precipitation is very uneven. High population growth areas are not necessarily the same places that have high precipitation. So if you look at this map, you can get a sense of where your area is and how much precipitation you get. So some places in the world are water rich in the terms that they have large flows of water, large fluxes, and some are water poor. They have low flows or low fluxes. And in some of these places, there are significant stocks of water. So it can be very tempting to use this stock rather than this flow of water to manage your society, to manage the needs of your society. If we are going to extract water from ground sources, we need to know where it is and how we can get it. It turns out that we think of the Earth as being this big ball of rock, and at the surface that is in a sense true, but rock actually does sometimes have spaces between the different rock granules or within the cracks, and so there's a pore space where this water can be held. If a water-bearing rock not only has some space to hold some water, but also lets water flow relatively quickly through it, we often call this an aquifer. An aquifer is an especially good groundwater source because if we dig a well or put down a pipe, we can quite easily extract water from this aquifer. Water will flow out of this aquifer quite well. If we pump out lots of water from an aquifer, this actually lowers the groundwater level. So the name for this actually is the water table. So the water table is the height at which point the rock is saturated with water. As we subtract water from an aquifer, that is, we take out water faster than it gets recharged through those natural hydrologic processes, the water table can drop. And of course, as it drops, we would need to dig deeper wells to extract the water. And eventually, of course, we could use all the water up because we removed the stock entirely. In an unconfined aquifer, water flows freely. So it flows because of gravity. It will always go downhill, just like water on the surface does, and eventually it will reach the oceans. Or it will flow down the rock column until it reaches the water table. If you look at some examples of this, what you'll find is that if we have layers of aquifers in a single place, the deeper the water, the older it tends to be. And this makes sense, of course, if we imagine that there was a river at the surface or a rainfall at the surface and water came through the rock from that, then it would be younger at the surface, and as it got deeper and deeper down to the earth, it would obviously be longer and longer since it was at the surface. So this is why some of these very deep aquifers are actually some of the oldest water. If we were just using fluxes, then we really wouldn't have major sustainability issues anywhere, because all the water we would be taking out would be replaced each year. That's a renewable use. But many places in the world are lowering water tables. In the United States, the Southwest is known as a place where there is a lot of withdrawal of water stocks. Phoenix is shown here, and actually aquifer levels in this area have dropped around 400 feet since industrial settlement. This is an unsustainable use of the water resource. So water is being subtracted much faster than the dry desert-like environments in many places in the Southwest can recharge that resource. So when that resource is exhausted, water use will have to change drastically. So in some ways, we can think about this in those J-curve models that we saw in the very first week. We can have an expansion in the amount of water use, but because this water use isn't sustainable, we could eventually hit a wall and we'd see it collapse. In fact, it turns out that some of the biggest countries in the world are not using their water sustainably. Countries like China and India have large populations and have intensive agriculture, And as we will see this week, agriculture is an enormous user of water. And so to feed these large populations in an effective and cheap way, it can often be one of the things that can be the cheapest thing to do is to over-extract water from groundwater sources, especially if groundwater sources are not properly priced or regulated. Already, in fact, many basins around the world are under stress. I have a map here, and if you look at this, you might see if you live in a region which is experiencing some stress. Here in the Midwest of the United States, there is some stress. In fact, the water table around Chicago has dropped enormously. But having said that, there's actually large flow rates here. So it's not so much of an issue that the flux rate is high enough that the recharge will replace what it's lost. But in some places around the world, the extraction rates is much higher than that natural recharge flux. So we can often see the impact of excessive water withdrawal at the surface. If you take a lot of water from the surface, or even if you take it from the subsurface, and that encourages water to percolate down as the water table is lowered, we can see lakes drying up. And this has happened in many places around the world. For example, Lake Chad in Africa has almost disappeared. Experts predict that the regions of water stress around the world will increase over the coming decades. And this is a combination of a number of factors, but the leading cause, of course, is that we have an increased population, and to feed an increased population, you need an expansion or an increase in efficiency in agriculture. Water is very important in efficient agriculture, so there'll be more pressure to extract more water to make more crops to feed more people. So how are we using all of this water in the Earth system? Well, it turns out worldwide the single major use of water is agriculture. We often think about wasteful water processes in industry or in the home, but for most countries, how we use water when we feed our crops is the single most important thing. So water loss during in agricultural processes is a far more significant problem than water loss in the home. It's not the case that all countries have agriculture as the #1 user of water. If you look at this map, you might see what your country uses the most. Interestingly, in the US, the single biggest user of water is electricity generation. But of course, a lot of this water is directly returned to the local hydrologic system. The water is only used briefly in cooling towers. In some countries, industry is very important, and in others, domestic use is very important. But on average, worldwide, agriculture is the #1 user of water. Again, most of the increase in water use is apparently occurring in countries that have increasing populations. Interestingly, just as we saw for energy, many of the more advanced countries, such as the United States, have actually seen a more efficient use of water over the last few decades. And in fact, despite an increase in population in the United States, water use has been flat for several decades. So it's not true that water use must inevitably increase, but it is true that if water use does increase by a lot, we will be using more and more stock, and we will be causing more and more water stress. We'll be opening ourselves up for the danger of a crash as we exhaust water reserves. So if many places are under water stress today, this additional use implies that there'll be even more places under water stress in the future. Some people have talked about water wars. My take is that we haven't seen water wars yet, so it's reasonable to expect that we won't really see them over the 21st century. Instead, because water is an important resource in the development of societies and nations, if countries are water constrained, we will see impoverishment and a lack of development. And this can contribute to civil and social problems, including conflict. So although I don't think water on its own is going to cause water wars, if you like, I do think it will contribute to unrest and potential conflict in the coming decades. There is a way around this problem of having water-stressed areas. It's not the whole world that will be water-stressed. Some countries have more water than they need. Cooperation is a way to share this water, and we will see in the next lecture how countries can work together to manage water resources.
Produced by OCE Atlas Digital Media at the University of Illinois, Urbana-Champaign.